Okay, so hello and welcome back. So now let's do the miscellaneous exercises on chapter 3. Let's do the miscellaneous exercises on chapter 3. So what we have is number one we have let A be a matrix as basically 0 1 0 0, and you want to show that A times I, A is some scalar plus B times A, and again B is a scalar, A is A, and I is the identity matrix, raised to the power n is equal to A raised to the power n times I plus NA plus n times A raised to the power n minus 1 into B into A, where I is the identity matrix, of order 2 and n belongs to the set of natural numbers. So this is the matrix that you have, and you want to show that A times I plus B times A raised to the power n is equal to A raised to the power n times I plus n times A raised to the power n minus 1 times B into A into matrix B, and then you add these two matrices together, and I is the identity matrix of order 2 and n belongs to n. So let's see how we can do that. So I think for this you need to use the method of mathematical induction, because there is no other way to do it as far as I do know. So again, the method of mathematical induction, as we discussed before, is that you need to basically show that P of 1 is true, and you need to show that you need to assume that P of k is true, and you need to show that P of k plus 1 is true. P of k plus 1 is true, and based on that conclude that P of n is true. That is the method of mathematical induction. So in order to do that, I'm going to show that P of 1 is true, meaning that basically when n is equal to 1, we have basically A times I plus B times A raised to the power 1, A times I plus B times A raised to the power 1 is equal to A raised to the power 1 times I plus n times n, as n is actually 1, so I don't really have to write it, but since I have written it over here, n times basically A raised to the power 1 minus 1 times B times A, and therefore you have AI plus BA is equal to A times I plus well, this is a 1, this is a raised to the power 0, which is equal to 1, and therefore you have b times a. So ai plus ba is equal to ai ba, right? And but of course this is true, which is true. Therefore p of 1 is true. Now we need to make the assumption that p of k is true. Okay. So now I will make the assumption that p of k is true. I will assume that p of k is true. That is basically a times I plus b times a raised to the power k is equal to a raised to the power k times I plus k times a raised to the power k minus 1 times b times a. So I'm assuming that this is true, right? And now I need to show that basically we need to prove that the tip of my pen is new, so it's not easy to write with it. It's very slippery. We need to prove that basically p of k plus 1 is true. That is basically a times I plus b times a raised to the power k plus 1 is equal to a raised to the power k plus 1 times a times I plus k plus 1 into a raised to the power k plus 1 minus 1 is equal to k times b times a. That is basically this. That is basically to show that this one is true. Okay, so now basically we want to show that p of k plus 1 is true. Now in order to show that p of k plus 1 is true, what I will do is that I will write p of k plus 1 is of course this equation over here. Now the LHS of p of k plus 1, is equal to ai plus b times a raised to the power k plus 1, right? I want to show that this is actually equal to this, right? Meaning that this equation is true. Now I can write this as basically ai plus b times a raised to the power k, and I have an expression for that here, times basically ai plus b times a, and that would be ai plus b times a raised to the power k plus 1, right? And that would be equal to basically this expression times this expression, because this is ai plus ba raised to the power k, which is basically this expression here, based on the assumption that we have made. So we have a times k, a raised to the power k times I, plus k times a raised to the power k minus 1, b times a, whole multiplied by basically a times a A times I, I'm sorry, A times I plus B times A. And believe it or not, well, I actually did basically test this using a couple of matrices. I put a couple of matrices together. I wouldn't believe that it would actually work. But it seems that it does work, meaning that if you have, for example, some matrix like, for example, A times, for example, some matrix A plus B times some matrix, for example, B, and if you multiply this by some matrix like, for example, C times some matrix C, and plus some D times some matrix D, what happens is that, of course, you can multiply this by matrix A, multiply this scalar by matrix B, multiply this scalar by matrix C, multiply this scalar by matrix D, add the two matrices together, and then you will end up with two matrices, for example, one matrix for this part and one matrix for this part. You can multiply them together and you will get one matrix, right? That you can do. But you can actually multiply these together the way that, for example, you are dealing with the real numbers, meaning that when you say you have A plus B times C plus D, when I'm dealing with real numbers, I can write this as A times C plus A times D plus B times, for example, C plus B times D. That I can do in the case of real. You can do the exact same thing over here. It actually, and it works. It took me about an hour or so. I solved the problem, and what I found out was that basically any one of the solutions that you use, either you do all of these operations on the matrices and then multiply the two matrices together or do them individually, you will actually get the same answer. And this is actually the way that the solution here works. So, which means that basically you can actually multiply all of these things together without worrying about anything, and it does actually work. Anyway, what that means is that this is A raised to the power k times, for example, let's say that you want to multiply this by this one. You have A raised to the power k times A, and that would be times I squared. I times I is equal to I squared. Then you can multiply this by this, which would give you basically A raised to the power k times B times, for example, I times, of course, the order of the matrices is important, meaning that you have to write this as I times A, not A times I. Of course, I times A and A times I would be the same, but then if you're dealing with two different matrices, where one of the matrices is not the identity matrix, then you have to take care of the order of the matrices, otherwise you would get something different. And then you have over here, if you multiply these two together, you'll get k times A raised to the power k minus 1, A raised to the power k minus 1 times B times A times A times I. And multiplying this by this, you will get basically k times A raised to the power k minus 1. Then you have times basically B and B would be B squared, and that is A squared. That's what you will end up with. And that is basically A raised to the power k times A is equal to A raised to the power k plus 1 times I squared. I think I squared is equal to, I'm not really sure what that is, but as far as I can remember, let's say that you have a 1001 times 1001, And if you do this multiplication, you get 1 times 1 is equal to 1 plus 0. And then 1 times 0 is equal to 0 plus 0. And then you will have 0 plus 0. And then you will have 0 plus 1. As I suspected, that is 1001, which means that I squared is actually equal to I. Even if you calculate I cube, you will end up with I. I raised to the power 4, you will end up with I. So I can write this as I. And then here you have, of course, I times A is again the same thing as A, right? But then you need to make sure that you're writing your expression based on what you have here. So I don't know what's going to happen as I simplify these things, but so let's see. I'm going to just write it as IA, and then in the end we will decide what we can do. So this is the same thing as A raised to the power K times B times IA plus, well, this is K times, for example, A raised to the power K minus 1 times AB, and if I multiply this A by this A raised to the power K minus 1, I will get A raised to the power K, and then I will have a B over here, and then I have A times I, and then I have K times A raised to the power K minus 1, and this is, so that is K times A raised to the power K minus 1 times B squared times A squared times A squared. Now, as you can see, this is A raised to the power K, and this is A times I. This is I times A. You can basically, and you have B over here. You have A raised to the power K over here. So you can take all of these out, meaning that I can write this as A raised to the power K times B times, for example, times A. And your goal is to write your equation somehow in this format. Here. So I'm going to write, so what I'm going to do is that I'm going to write this as simply A raised to the power K times B times A plus K times A raised to the power K times B times A. I'm just going to forget about the i's, because when you multiply them, you'll get the same thing. And then here I can take A raised to the power K, B raised to B times A. I can take that out. And write this as A raised to the power K, B times A. Can take that out, and then I can write this as 1 plus K. So these two terms added together will give you this one. So I'm going to write this thing over here. So that is K plus 1 plus K plus 1 times A raised to the power K times B times A, and this is A squared, right? Okay. Now, what I have here is that k times a raised to the power k minus 1 times b squared times a squared, and over here I have a raised to the power k plus 1 times I. And what that means is that I need to end up with basically this. I need to end up with this. Basically with this expression here. To be more specific, I need to end up with the right hand side of this. So a raised to the power k plus 1 times I already have it. Now out of these two, I have to make k plus 1 times, actually I have to write this way. This has to be in parentheses, right? So k plus 1 times a raised to the power k times b times a. And somehow this term must be I think if you calculate a squared, you will end up with something with a zero matrix. You see over here, if you calculate a squared, you will have basically 0, 1, 0, 0 and times 0, 1, 0, 0, and you will have basically 0 times 0 is equal to 0, and 1 plus 1 times 0 is equal to 0, and then 0 and 0, and then 0 and 0, and then 0 and 0. So you will end up with the zero matrix. So this whole thing becomes 0, right? So then a squared is equal to 0, and therefore you can write this as a raised to the power k plus 1 times I plus k plus 1 times a raised to the power k times b times a. And that is the same thing as basically the LHS of this, which is actually equal to a raised to the power k plus 1 times I plus k plus 1 times a raised to the power k, which is equal to the RHS. And therefore P of k plus 1 is true. P of k plus 1 is true. Right? Since P of k plus 1 is true, so the result is true for n is equal to k plus 1. And so, hence by the principle of mathematical induction, A of I raised to the power n, you can say that basically you can say that P of n is true. You can say that P of n is true where, for example, where P of n is equal to is the same thing as a times I plus b times a raised to the power n is equal to a raised to the power n times I, a raised to the power n times I, plus n times, for example, n times, well, a raised to the power n minus 1 times b times a times b times a. So that's basically how you prove this thing. This exercise, this one single exercise, this cost me around 2 hours. I worked on this exercise for 2 hours. Okay. The second one is another such exercise, and you want to prove the same thing for another matrix.